We continue discussing dynamical systems by considering ergodic theory. So, this lesson presents a systematic introduction to invariant measures, ergodicity, mixing, acerbic measures, time versus ensemble averages with theory and computational examples. So, first of all, the motivation behind this. Ergodic theory studies the long-term statistical behavior of dynamical systems. So, you have a system and it behaves in a particular way every time. So ergodic theory simply tells us the long-term statistical behavior of such dynamical systems. So instead of tracking individual trajectories, we study averages and distributions. And the main question is, do time averages along trajectories agree with spatial averages over the state space? Now that may sound like a lot of grammar, but the fact is this. Grammar in quotes now, that is in the Nigerian context. Now, the simple idea behind ergodicity is the fact that if you toss if you toss a coin 1,000 times, it will behave like when you toss 1,000 coins at once, something like that. So ergodicity gives us the average behavior of dynamical systems, of whatever system you're looking at, right? Okay, so like again, we said the main question is, do time averages along trajectories agree with spatial averages over the state space? Now let's go for it. Of course, as we've been talking about dynamical systems, uh, and dynamical system simply talk, so any measure, right? A measure preserving dynamical system is a quadruple. So a measure preserving dynamical system is a quadruple having x, b, mu, and t, where x is the state space, beta is a sigma algebra, mu is the probability measure, and t is the evolution map, right? T maps the state space to itself, and it is the evolution map. And then we have iterations like, starting with x, we have t of x, t squared of x, t cube of x, talking about different time steps like that. Because we know, generally speaking, that dynamical systems are systems that evolve over time, they change over time, they decrease, they increase, all kinds of things happen over time. Those are dynamical systems. But when we talk about ergodicity, we are talking about a measure of statistics. That is why you can see talks about probability measure, sigma algebra, and all of that. Okay, we have an example right here. You have a logistic map. We studied the logistic map. T of x equals 4x into 1 minus x, with x bounded from 0 to 1. This system is chaotic and statistically stable. All right. Now, the deal is, we've been talking about logistic maps a whole lot in this whole thing. In fact, it's the most talked about model we've been talking about, as far as dynamical systems are concerned. And now we're talking about ergodicity, and it is known that this particular system, though it is chaotic, it is statistically stable. And then we have the representation right here. So we define a function logistic which takes the parameter x and returns 4x into 1 minus x, just like we describe right here. And then we do 5,000 iterations like that. So after 5,000 iterations, then we'll see how the system is stable or not. But of course, we know already that this one is stable. So we take our initial guess to be 0.3, of course, which is well between 0 and 1. Okay, so we move on for to look at this now. So then we'll see the orbit of the logistic map, and we'll see how it is, though chaotic, but stable over time. But statistically stable. So we see chaos here, but then it has a particular pattern we can see in how it goes, right? So then we go ahead to talk about invariant measures. All right, a probability measure, mu. Okay, we can see all of this together at once. A probability measure mu is invariant under t, that's under time now, if the mu of t inverse of a is equal to mu of a for all measurable sets a, right? So the mu of t inverse of a is equal to mu of a, for all measurable sets a, right? And the interpretation of that is that the probability distribution is preserved by the dynamics. So, and then invariant density of logistic map for t of x equals 4x into 1 minus x, which we saw the other time, which is though chaotic but statistically stable. The invariant density is given as rho of x equals 1 over square root of pi square root x into 1 minus x. And this is the system's equilibrium distribution. All right. So, and then we can, of course, see that, this is based on what we had seen, the system we set up before. So we just want to see a histogram that shows the invariant density approximation. Of course, between 0 and 1, we have the system bounded between 0 and 1, and then we have the density approximation shown this way. And then we move on to talk about the idea of ergodicity itself, which we've been talking about. A system is ergodic if every invariant set has measure 0 or 1. So every invariant set has measure 0 or 1. Equivalently, we say that time averages equal space averages. So time averages equal space averages. Another idea to the another explanation to the idea that when you toss a coin 1,000 times, that's you can approximate that by tossing 1,000 coins at once. Okay, so time averages equal space averages. So talking about the Beckhoff ergodic theorem, if T is ergodic and F belongs to L1 of mu, then we say that the limit as n approaches infinity of 1 over n multiplied by the summation from k equals 0 to n minus 1 of f into t raised power k of x is the integral of f d mu, basically, for almost every x. And this is the Beckhoff ergodic theorem for almost every x. And then we can do that representation here. We have f is equal to x. Imagine f is equal to x, and we define lambda x as x, right? That means we're saying f is equal to x, and the time average is actually np accumulation sum of f of x divided by the range, a range from 0 to n plus 1. And then we plot the time average, and we see the time average convergence like this. So we print the time average and space average also, and we see how if they are close by exactly. So in this case now, we have the time average convergence represented in this graph like this. Okay, and interestingly, you see the final time average is 0.50174, blah blah blah, and then the space time average is about the same thing. In fact, up to how many decimal places? 3, 6, 9, 12, 15. Correct to the 15th decimal place, as you can see. So that gives a very good averaging, and that is the whole idea of ergodic theory. That the question time averages equal space averages, basically, and that's what we see right here. That final time average is about the same thing as space average. In fact, it correct to the 15th decimal place. Now we have non-ergodic example, like when we have a rotational rotation, irrational rotation, I mean, irrational rotation. If you consider t of x equals x plus alpha mod 1, if alpha is rational, orbits are periodic and not ergodic. So in this case, imagine this. We define a function called rotation, which takes parameters x and alpha and returns x plus alpha mod 1. So whatever this gives us mod 1, so we divide by 1, whatever is left. Of course, when you divide something by 1, it remains itself, sort of. Okay, so n, we have 1,000 iterations. We have the initial value, of course, to be 0 0.1, and then for I in range 1 to n, we have x over I rotation. So we run it over all of that, and then we have this whole thing. So we have this now. See just what happens. We have 0 0.1 and 0 0.6 up there. So that takes us to the concept of mixing. So a system is mixing if the mu of t raised by minus n a intersection b simply means mu a multiplied by mu b as n approaches infinity. So this simply tells us that mixing implies loss of memory. So mixing means there's a loss of memory, and we have a correlation function for observables f and observables fg. C of n is equal to integral of f dot g composed with t power n d mu minus integral of f of du integral g du, and mixing applies if cn approaches 0. So if this whole setup approaches 0, then we say there's a loss of memory, and that means there is mixing. So we can, we have a Python code to talk about that. Okay, it's a pretty long one, so I'll try to just skim through it bit by bit and see how we have that. So here we have a ergodic theory logistic map for a complete demonstration now. So we have the logistic map definition, which is 4x into 1 minus x. Then we generate a long orbit. We have length of orbit is large for statistics. That's n is 10,000. X is zeros, in n places. And then we have the initial condition, which is 0 0.3. Oh, I said initial value the other time. So for I in range 1 to n, we have xi equals logistic x I minus 1. And then we print orbit length, that's length x. And then we plot first part of orbit that we have logistic map, that's first 500 iterates. Okay, and then we remove the transient here. We have data x 2000 to the end, and m is length of the data. Then we print data length after transient like that. And then we define observables. For f, we have lambda x, which is x. So we define f as x, and we define g as x squared, because lambda is a yeah, we have lambda functions in Python. So if you check my playlist on Python basics, you'll see lambda functions there. And we have compute correlation function. You have max on the score, which is minimum of 200, comma m uh, double backslash 2. That's integer division. So at the end, in this particular division gives us the integer value, and we don't care about the remainder. Then we have min f, which is np min f data, min g, np min g data, and we have this whole setup. We have the correlation for k in range, 1 to maximum of k. You have this whole setup, and we append the correlation step by step like that. So you have the correlation, np correlation. You have correlation again, correlation is none, and all that. Then you have other things like you have correlation points. Then plot correlation decay. We have correlation decay plotted here. See, the plot is about the correlation. We have marker 0 and marker size is 3. Then we have all the labels. Then we have time versus ensemble average, set up right here. So we talked about the average, time average and space average the other time. So something like that. And then of course we have some values that are like diagnostic values for this kind of system. So with that now, first of all, we have so see the first plot here. We have an orbit length of 10,000. So for the first 500 iterates, we have this. We have this one. And data length after transient is 8,000. Correlation point is 199. And next, we also have the correlation decay for logistic map where R is equal to 4. We have this kind of system. We have the lag K this way, and we have C of K this way. The other time we were talking about C of K approaching 0. Okay, and that's like the mid value around here. That's Cn approaching 0 there. So in this case now, we have time versus ensemble average. So time average is like what is happening right now. Ensemble average is what you do over time or something like that. Okay, time average is what is happening over time, and ensemble average is like when you do everything at once. It's more like when you toss a coin 1,000 times. That's like the time average. But then when you toss 1,000 coins at once, that's the ensemble average. So for the time average, we have 0.0019, like that. And for ensemble average, we have 0.00025. There's a bit of gap right there. Okay. Then of course we have all this interpretation. We see that the orbit is chaotic. Correlations decay implies mixing. Where's the correlation decay here, by the way? Yeah, we have the correlation here. Okay. So correlation decay implies mixing because we have the whole thing hovering around 0. Okay. So and then time average is approximately ensemble average, and that implies ergodicity. So I mean, this is approximately 0.00. So to three decimal places we have 0.0002. But here to three decimal, yeah, I mean the gap is a bit wide, but at least it's still small in a sense, right? So and then this indicates existence of SRB measure. Now this is the first time SRB measure is coming up in the lesson, apart from when I introduced it. So let's talk about SRB measure then. SRB, which is Sinai-Ruel-Bowen measures, describe physically observed statistics, and they satisfy 1 over n summation from k equals 0 to n minus 1 of f t raised by k t raised by kx, implying integral of f du SRB. Okay, so for most initial conditions, so they describe physically observed statistics. So we have something like that here. We have convergence to SRB measure. So here we define an orbit with the initial condition, and we have 5,000 iterations, and we have x is zeros. So x of 0 is x naught, and we define the logistic. Xi is logistic, xi minus 1, and we return this. So we do this for different initial conditions, 0 0.1, 0 0.3, and so on and so forth. Then we see the convergence to SRB measure when we run this code, and this is what we have for that. Okay, I think it bears a bit of resemblance with what we saw the other time, when we started out. Then we have time versus ensemble averages. Of course, this is where the ergodicity idea is emphasized again. So we have time average, what happens over time, and then ensemble is like what happens at once, to see if the two approximates are about the same. So for the time average, we have f sub t of x bar equals 1 over n summation k equals 0 to n minus 1 f into t raised per kx. So ensemble average, we have this now to the integral of f d mu. So ergodicity implies equality of both the time and ensemble averages. So we have this right here. So we have a comparison code for the time and ensemble average. So we have a function defined as sine 2 pi x, right? So the time average, we have np dot com sum of this f of x now all over for that whole range we have there, and then the ensemble average is just np mean of all the everything at once. So time average is what happens one after the other. You sum it up and average, but ensemble average is what happens just at once. All right, and then you plot time average, and then you have the x-axis line. You have ensemble average in color red, and then you print all this now. So see what you have here. You have again the one in red, like we know is the ensemble average. So and the other one is the time average. The blue one is the time average. So like I said, you want to see the time average as the average of what happened one after the other. Like when you toss a coin 1,000 times, but the ensemble average is when you toss all the coins, when you toss 1,000 coins at once. Okay, so that's like that. Okay, like here now we have to three decimal places, it's like roughly zero, or maybe should we do four decimal places? One, two, three, four. To four decimal places, that's like 0.002. To four decimal places, that's like 0.00005, like that, right? So some kind of closeness there. Then we have a non-ergodic average in this case. Now, when we try it this other way, and then you see it doesn't behave like the other one. Okay. So in summary, we see the concept of invariant measure, meaning probability is preserved. We see ergodicity, meaning that time average is equal to space average. That is, when you what you get, the results you get when you toss a coin 1,000 times is the same thing. Is that about the same thing you get when you toss 1,000 coins at once? Then you have the mixing, which talks about memory loss, and then you have SRB, which talks about physical distribution. Then you have the time average along trajectory, and then some average over space. So we're saying that time average along trajectory is approximately ensemble average over space. So the hierarchy, we have mixing implying ergodicity and ergodicity implying invariance. Okay. All right. So for final remarks now, we have that ergodic theory explains why deterministic systems exhibit stable statistics. Then it justifies statistical mechanics, chaos theory, and stochastic modeling. The key idea is that long-term averages become predictable. All right. So, I mean, in the case of the tossing of coins I've been talking about, it can be predicted that as you have many, many coin tosses, you have average of close to 50% head and 50% tails the more as the experiment continues. So it converges towards H. I'm talking about tossing fair coins, by the way. So you end up having roughly 50% of heads and 50% of tails. So solve the following problems using theory and computation where appropriate. You have problem one, invariance measure. Let T of x be 3x mod 1 on 0, comma 1. Show that Lebesgue measure is invariant under T. I mean, just try this out. You have computing and invariant density for number two. So the two of them look like about the same thing. Then for testing ergodicity, now prove that T is ergodic if alpha is irrational. Simulate cases for rational and irrational A. Compare time averages. Then time versus space averages for the logistic map T of x equals this and f of x equals x squared. Compute the time averages, compute ensemble averages, compare convergence rates. So you can use some of the codes I had used before. Then for 5 and 6, we have correlation decay. So compute these correlations, use f of x equals x. I think we did something like that already. So you just want to look at that and modify. Then mixing and ergodic. Find an example of a map that is ergodic but not mixing and just mixing. So justify your answers theoretically and numerically. So then we have SRB measure Bayesian. For the logistic map, choose at least 10 random initial points, compute long-term histograms, show they converge to the same distribution, estimate Bayesian size. And then we have it. Failure of ergodicity. Consider T of x equals x mod half. Describe the invariant set. Show that T is not ergodic and compute time averages. Then for 9 and 10 now, you have, can I show everything at once? So for 9 and 10, you have ergodic decomposition, okay? And then um, You also have physical interpretation. Consider a gas modeled by a chaotic billiard. Explain why ergodicity is important. Describe how SRE measures appear. Relate to temperature and pressure. Discuss limitations of the ergodic hypothesis. Then instructions. Provide mathematical justification where required. Include Python simulations for numerical parts. Compare theory and experiment. Comment on convergence behavior. So you can actually check out you can check the codes that can also help you to answer some of these questions. So some of these questions are basically repetition patterns of the same things I've been explaining. So with this, I come to this end. To the end of this interesting video about ergodic theory. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Don't forget to try your hands on the problems and see how well you get the gist. So you can look at the examples to solve the problems. If you have subscribed already, I must thank you very much for doing that. If you haven't subscribed, I wonder what exactly you're waiting for. Why not go ahead, subscribe and hit the notification bell so you can always get alerted each time a new video is released. Can also take it a step further by clicking on join. All right, that gives you the opportunity to have some special privileges, some perks like that associated with being a member, like being the only one seeing some videos or being the first to see some videos before others see them. Hanging out with me, having me, put you through certain things as it relates to the things I do on this channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again. Keep doing math right. Bye.